Welcome! Today, we will explore an interesting problem from LeetCode, problem number 1394, find lucky integer in an array. In this problem, we aim to identify a lucky integer in a given array, an integer that matches its frequency within the array. We'll dive into various approaches to solve it and analyze their complexities. Let's get started. In this problem, we are tasked with finding a lucky integer in an array. A lucky integer is defined as an integer in the array where its frequency in the array is equal to its value. For instance, if the integer 2 appears exactly 2 times in the array, it would qualify as a lucky integer. The goal is to return the largest lucky integer in the array. If no such integer exists, we return -1. The input is an integer array ARR with a size ranging from 1 to 500, and each element in the array is guaranteed to be between 1 and 500. The output is a single integer, either the largest lucky integer or -1 if none exist. Let's look at some examples to better understand how this works. In the first example, the input array is 2, 2, 3, 4. The output is 2. Here's why: the integer 2 appears exactly 2 times in the array, and since its frequency matches its value, it qualifies as a lucky integer. On the other hand, the integers 3 and 4 do not meet this criterion, as their frequencies do not match their values. Therefore, the largest lucky integer in this array is 2. Now consider a second example with the input array 1, 2, 2, 3, 3, 3. The output in this case is 3. Here's the reasoning for the second example: the integer 1 appears exactly once, so it qualifies as a lucky integer. Similarly, the integer 2 appears twice, and the integer 3 appears 3 times, so both of these also qualify as lucky integers. However, since we are looking for the largest lucky integer, we return 3. Moving on to another example, consider the input array 2, 2, 2, 3, 3. In this case, the output is -1. Here's the explanation for why the output is -1 in this example: the integer 2 appears 3 times, but its frequency does not match its value. Similarly, the integer 3 appears 2 times, which also does not match its value. Since there are no integers in the array where the frequency equals the value, there are no lucky integers. As a result, we return -1. Let's now discuss some constraints and edge cases to consider for this problem. The array size is guaranteed to be between 1 and 500, and each element is between 1 and 500. Some important edge cases include arrays with no lucky integers, such as 2, 3, 4, where the output would be -1. If there are multiple lucky integers, like in 1, 2, 2, 3, 3, 3, we return the largest one, which in this case is 3. For arrays where all elements are the same, like 4, 4, 4, 4, we check if the frequency matches the value. Here, the output would be 4. For a single element array, such as 1, we return the element if its value matches its frequency, otherwise, we return -1. To solve the problem of finding a lucky integer in an array, we first considered the brute force approach. The intuition here is straightforward: we iterate through the array, and for each unique number, we count how many times it occurs. If the number equals its frequency, it qualifies as a lucky number. To implement this, we start by iterating through the array to collect all unique numbers. Then, for each unique number, we perform another loop to count its occurrences. If the number matches its frequency, we check if it's the largest lucky number we've encountered so far. Although this approach is simple to understand and implement, it's computationally expensive due to the repeated counting of frequencies for each number. This results in a time complexity of n squared, which makes it inefficient for large arrays. On the upside, it has minimal space requirements since we don't use any additional data structures, but the trade-off is a lack of scalability for larger inputs due to the nested iteration process. A more efficient method is the optimized approach using a frequency map. The key idea is to count the frequency of all numbers in the array in a single traversal and store these counts in a hash map. By doing so, we avoid repeatedly recalculating frequencies. The frequency map allows us to directly check if a number is lucky by validating the condition that the number equals its frequency. To implement this, we first create the frequency map by iterating through the array and counting occurrences of each number. Then, we iterate through the map and check if the key equals its value. While iterating, we also keep track of the largest lucky number. This approach is highly efficient, with a time complexity of O(n) for counting and checking, and it scales well even for large arrays. The trade-off is the additional space required for the hash map, which grows with the number of unique elements. However, this is a worthwhile trade-off given the significant improvement in runtime efficiency compared to the brute force method. Another alternative we considered is the sorting-based approach. The intuition here is that sorting the array groups identical numbers together, making it easier to count their frequencies. Once sorted, we can iterate through the array, counting the frequency of each number. If a number matches its frequency, we check if it's the largest lucky number we've found so far. The sorting step has a time complexity of O(n) log n, and the subsequent iteration to count frequencies is O(n), resulting in an overall complexity of O(n) log n. This method doesn't require extra space beyond the input array, as sorting can be done in place. While simpler to implement than the frequency map approach, it's slower due to the sorting step. Ultimately, this approach is less efficient for very large inputs, but for smaller arrays, it can be a viable alternative. After comparing all three methods, we selected the frequency map approach as the final solution because of its linear time complexity and ability to handle large arrays more effectively. The key insight, or aha moment, was recognizing that a hash map allows us to separate the process of counting frequencies from the lucky number verification. This decoupling enables us to solve the problem in linear time, as we avoid redundant calculations. By iterating through the frequency map rather than the array itself, we can directly track the largest lucky number without needing nested loops or sorting. While the frequency map approach does require additional space, this is a reasonable trade-off given the significant reduction in time complexity compared to the brute force approach. On the other hand, while the sorting-based method uses less space, its O(n) log n time complexity makes it less ideal for large inputs. Ultimately, the frequency map approach strikes the best balance between efficiency and clarity, making it the most scalable and optimal solution for this problem. The problem find lucky integer in an array challenges us to find the largest lucky integer in a given array. A lucky integer is defined as a number whose frequency in the array matches its value. For instance, consider the input 2, 2, 3, 4. Here, the number 2 appears exactly 2 times, making it a lucky integer. Since there are no other numbers in the array that satisfy this condition, the output is 2. If no such number exists in the array, we return -1. This problem requires us to efficiently count the occurrences of each number and determine if any of them meet the lucky condition. To solve this problem, we use a hash map for efficient frequency counting and lookups. The first step involves initializing a frequency counter. The reason we do this is to record the occurrences of each number in the array without repeatedly traversing the data. We create an empty dictionary called frequency and traverse the input array. For each element, we increment its count in the dictionary. Once the frequency counter is built, we move to the next step, iterating through the frequency map. The goal here is to identify numbers where the value matches their frequency. To do this, we initialize max_lucky to -1, which will serve as our default value if no lucky integer is found. Then, we iterate through each key value pair in the dictionary. For each pair, we check if the number equals its frequency. If it does, we update max_lucky to the maximum of its current value and the lucky number. After processing the frequency map, the final step is to return max_lucky. If any lucky integers were found, this variable will hold the largest one, otherwise, it remains -1, which we return as the result. There are a few key insights to note here. First, using a hash map allows us to count frequencies in O(n) time, as hash table operations like lookups and updates are constant time. Second, the largest lucky integer is identified in a single pass through the hash map, making the approach efficient. Lastly, we need to handle edge cases. For example, if the input array is empty, we immediately return -1. Similarly, if the array contains no lucky integers, the algorithm ensures -1 is returned. If there are multiple lucky integers, the algorithm guarantees that the largest one is selected. The two primary data structures used in this algorithm are a dictionary and a variable. The dictionary, or hash map, is used to store the frequency of each number because it provides constant time lookups and updates, making it highly efficient for this purpose. The variable max_lucky is used to track the largest lucky integer found during the iteration. Now, let's analyze the complexity of the solution. The time complexity is O(n). This is because counting frequencies involves a single traversal of the array, and iterating through the frequency map is proportional to the number of unique elements, which is at most n. As a result, the operations combine to O(n). The space complexity is O(m), where m is the number of unique elements in the array. This space is used to store the frequency map. Let's walk through an example to see the algorithm in action. For the input 2, 2, 3, 4, we first construct the frequency map by traversing the array. The result is 2-2, 3-1, 4-1. Next, we find the largest lucky integer. Checking the number 2, we see that its value matches its frequency, so max_lucky is updated to 2. The number 3 does not satisfy the condition since 3 is not equal to its frequency of 1. Similarly, 4 is also not a lucky integer. Therefore, the result is max_lucky equals 2. Now consider an edge case with the input 1, 2, 3, 4. The frequency map becomes 1-1, 2-1, 3-1, 4-1. Among all the numbers, only one satisfies the lucky condition, so max_lucky is updated to 1. The output in this case is 1. For the edge case where the input array is empty, the frequency map is also empty since there are no elements to process. Without any numbers to check, the algorithm directly returns -1, as no lucky integers can exist in an empty array. This ensures that the solution handles all scenarios gracefully, including cases with no input data. This Python implementation solves LeetCode problem number 1394, find lucky integer in an array, by identifying the largest lucky integer in the input array. A lucky integer is defined as a number whose frequency in the array equals its value. Explanation of the code. 1. Importing dependencies. The counter class from the collections module is imported to efficiently calculate the frequency of each integer in the input array. 2. Class definition. A solution class is defined, containing the findLucky function, which serves as the solution entry point. 3. Counting frequencies. The counter class is used to count the occurrences of each integer in the array. The result is stored in the frequency variable as a dictionary-like structure, where keys are numbers and values are their frequencies. 4. Finding lucky integers. An empty lucky_integers list is initialized to store numbers that qualify as lucky integers. A for loop iterates through the frequency dictionary, checking each key value pair, number, count. If the number equals its frequency, count, it is appended to the lucky_integers list. 5. Finding the largest lucky integer. If lucky_integers is non-empty, the max function is used to determine the largest lucky integer. If no lucky integers are found, the function returns -1. Algorithm complexity. Time complexity, O(n), where n is the size of the input array. Counting frequencies with counter takes O(n), and iterating through the frequency dictionary is O(k), where k is the number of unique integers, k equals n. Space complexity, O(k), for storing the frequency dictionary. Example walkthrough. Input 2, 2, 3, 4. Frequency map 2, 2, 3, 1, 4, 1. Lucky integers 2, 2 appears 2 times. Output 2, largest lucky integer. Input 1, 2, 2, 3, 4, 4, 4, 4. Frequency map 1, 1, 2, 2, 3, 1, 4, 4. Lucky integers 1, 2, 4. Output 4, largest lucky integer. This implementation is clear, efficient, and adheres to the problem constraints. Here, we start by importing the necessary libraries and defining our class and method. The method findLucky takes an integer array as input. To solve the problem, we first create a frequency map using a hash map, which will store each number in the array as a key and its frequency as the associated value. We populate this map by iterating over the array, using the getOrDefault method to handle cases where the number is not yet in the map, incrementing the count for each occurrence. After constructing the frequency map, we initialize a variable largest lucky to -1, which will store the largest lucky integer we find. A lucky integer is defined as one whose value is equal to its frequency in the array. Next, we iterate through the entries in the frequency map using a for each loop. For each entry, we extract the key and the value, representing the number and its frequency, respectively. We then check if the number equals its frequency. If this condition is true, we update largest lucky to be the maximum of its current value and the number. This ensures that we always keep track of the largest lucky integer. Finally, after completing the loop, we return largest lucky. If no lucky integer exists, the method correctly returns -1, as initialized at the beginning. Here, we are solving the problem using a basic example where the input array is 2, 2, 3, 4. The first step is to calculate the frequency of each number in the array using the counter class from the collections module. This gives us a frequency map, 2, 2, 3, 1, 4, 1. Next, we initialize an empty list called lucky_integers to store any number that qualifies as a lucky integer. Now, we iterate through each key value pair in the frequency map. For the number 2 with a frequency of 2, since the number equals its frequency, we add it to the lucky_integers list. For the numbers 3 and 4, their frequencies do not match their values, so we skip them. After completing this iteration, the lucky_integers list contains just 2. Finally, we identify the largest lucky integer in this list, which is 2, and return it as the output. In this example, the input array is 1, 2, 2, 3, 3, 3. Starting again, we compute the frequency map of the array, resulting in 1, 1, 2, 2, 3, 3. We initialize an empty list called lucky_integers to store lucky integers. Next, we iterate through the frequency map. For number equals 1 and count equals 1, since the value equals the frequency, we add 1 to the lucky_integers list. For number equals 2 and count equals 2, the same condition holds true, so we add 2 to the list. Finally, for number equals 3 and count equals 3, the number matches its frequency again, so we add 3 to the list. At this point, the lucky_integers list contains 1, 2, 3. To determine the result, we find the largest value in the list, which is 3, and return it as the output. Now, with the input array 5, 5, 5, 5, 5, 6, 6, 6, 6, 6, 6, we start by calculating the frequency of each number, yielding the frequency map 5, 5, 6, 6. We then initialize the lucky_integers list as an empty list. As we iterate through the frequency map, we first encounter number equals 5 and count equals 5. Since the number matches its frequency, we add 5 to the lucky_integers list. Next, for number equals 6 and count equals 6, the condition is satisfied again, so we add 6 to the list. At the end of this process, the lucky_integers list contains 5, 6. To identify the result, we select the largest value in the list, which is 6, and return it as the output. To analyze the time complexity of our solution, we can break it into 3 main steps. First, we use the counter class from the collections module to count the frequency of each number in the input array. This step involves iterating through the array once, so it has a time complexity of O(n), where n is the length of the array. Next, we iterate through the frequency map using the frequency.items method, which provides key value pairs for each unique number and its frequency. The frequency map can have at most k entries, where k is the number of unique elements in the array. In the worst case, k can equal n, and since each comparison is constant time, this step also has a time complexity of O(k). Finally, if we find any lucky integers, we use the max function to identify the largest one. The max function iterates through the list of lucky integers, which can have at most k elements, so this step is also O(k). Together, these 3 steps form the basis of our time complexity analysis. When we combine the time complexities of these steps, we get O(n) for counting frequencies, O(k) for iterating through the frequency map, and O(k) for finding the maximum lucky integer. Since k, the number of unique elements, is bounded by n in the worst case, the overall time complexity simplifies to O(n). Now, let's look at the space complexity. The two main data structures used are the frequency dictionary and the list of lucky integers. The frequency dictionary, implemented using a counter object, stores one entry for each unique number in the array. In the worst case, where all elements in the array are unique, it will have n entries, leading to a space complexity of O(k), which simplifies to O(n) when k equals n. Similarly, the lucky underscore integers list stores the numbers that meet the lucky integer criterion. In the worst case, all k unique numbers could be lucky, so this list also requires O(k) space, which again reduces to O(n) in the worst case. Additionally, the algorithm uses a constant amount of auxiliary space for variables like number, count, and other intermediate values. This constant space contributes O(1) to the overall space complexity. When we combine the space requirements of the frequency dictionary, the lucky integers list, and the auxiliary variables, the total space complexity is O(n). To put this into perspective, let's compare this with a brute force approach. A naive solution would involve iterating through the array for each unique number to count its occurrences and check if the number equals its frequency. This approach would require O(n) squared time in the worst case, such as when all elements are unique. However, the space complexity would remain O(n), since we still need to store the unique numbers in a set or a list. Our optimized solution, by using a hash map to count frequencies in O(n) time and making a single pass through the unique numbers, reduces the time complexity to O(n), while maintaining the same O(n) space complexity. This makes it significantly more efficient. Now, let's analyze the algorithm across different cases. In the best-case scenario, where the array contains repeated elements but no lucky integers, all steps of the algorithm still execute in O(n) time. For the average case, when the array has a mix of lucky and non-lucky integers, the time complexity remains O(n), as frequency counting and dictionary traversal dominate the runtime. In the worst case, where all elements are unique, the time complexity remains O(n), and the space complexity is also O(n), due to the size of the frequency dictionary. To understand why this is optimal, consider the mathematical proof. Both frequency counting and dictionary traversal involve a single pass over the input array or the dictionary, respectively. These operations scale linearly with the input size n, ensuring that both time and space complexity are O(n). This makes the solution efficient and well-suited for the problem at hand. When working on this problem, there are several common mistakes to be mindful of. First, not handling edge cases can be a major pitfall. For instance, you might encounter an array like 2, 2, 3, 3, where no lucky integers exist. In such cases, your solution should gracefully return -1 rather than failing or producing incorrect results. Another mistake is using inefficient frequency counting techniques, such as calling list.count x inside a loop. This leads to an O(n) squared time complexity because the array is traversed repeatedly. A better approach is to use a hash map to count frequencies in a single O(n) pass. Additionally, it's crucial to ensure your comparison logic is correct. Value must equal its frequency, not greater than or equal to it, and certainly not any other condition. Overlooking this can lead to subtle bugs. If multiple lucky integers are present, don't forget to return the largest one. This often requires sorting or careful iteration to track the maximum value. Finally, avoid overcomplicating your solution with nested loops or too many conditionals. Often, a clean hash map implementation is the most efficient and easiest to debug. Now, let's explore how this problem fits into an interview setting. Mastery of hash maps is key here, as the problem heavily relies on using them for efficient frequency counting. Make sure you're comfortable iterating through hash maps and extracting key value pairs. Additionally, edge case awareness is essential. Interviewers might ask how your solution handles scenarios like empty arrays or arrays where all elements have unique frequencies. Another important aspect is optimization. While it's okay to start with a brute force solution, interviewers will want to see you recognize its inefficiency and quickly pivot to a more optimized approach. This demonstrates your problem-solving skills and adaptability. Be prepared for follow-up variations as well, such as being asked how your solution changes if the array is already sorted or if memory is limited for very large arrays. These follow-ups test your ability to adapt your approach to different constraints. For further practice, you can explore related problems like LeetCode number 697, which also involves frequency counting, or number 451, which combines frequency counting with sorting. Other examples include number 1165 and number 387, both of which focus on hash map usage in different contexts. Finally, let's discuss some alternative approaches to solving this problem. One option is the sorting-based approach. Here, you sort the array first and then iterate through groups of identical elements to count their frequency. This method has a time complexity of O n log n due to the sorting step, and while it's simpler to implement, it's not as efficient as the hash map approach for larger arrays. Another alternative is the two-pass hash map technique, where the first pass calculates frequencies, and the second pass identifies the largest lucky integer. This approach has an overall complexity of O n, and is slightly more readable than a single-pass solution, though it does require traversing the array twice. Lastly, there's the set-based filtering method, which involves using a set to filter out non-lucky integers. This still has a similar complexity to the hash map approach but can be a bit less intuitive, especially for beginners. Each of these methods has its trade-offs, so it's important to choose the one that best fits the problem constraints and your comfort with the implementation. Great job! Today, we solved the find lucky integer in an array problem using an efficient approach with hash maps. We reviewed its time and space complexity, discussed the importance of edge case handling, and highlighted key takeaways. Keep practicing similar problems to sharpen your skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!